we have seen different kinds of valves and we have seen how they are actuated. We have also seen that that they can be interfaced to for sophisticated actuations, especially continuous movements. They can be also driven by things like microprocessors. Now, while microprocessors can provide logic, sometimes simple logic can be provided by also by pneumatic elements. So, this is required in some specific cases, especially where you have big fear of explosion from electric devices, like let's say a natural gas plant. There using electric devices must be done with a lot of precaution, because one single spark may cause a big fire hazard and explosion. Similarly, there are in some cases there are very hot environments where maintaining any kind of electric insulation is a problem. So, therefore, in such applications, sometimes if the control logic complexity is not too high, one tends to use pneumatic logic. So, so pneumatic logic, no, just a moment. Okay, so we are back. So, okay. So, pneumatic logic means that we are basically trying to realize some sort of a digital logic. So, we need elements such as OR, we need elements such as AND. So, for example, if we can have OR logic, which will require pressure at either end for the air to flow into the system, pilot pressure. Similarly, if you have AND logic, then you will require pilot pressure to be applied at both ends simultaneously for the airflow to be connected to for the pump to be connected to the load. So, sometimes this AND logic is used for safety applications where the operator is forced to press both push buttons, so that his hand, where it is operating, pneumatic systems are very much used to assist operators in operating various kinds of machines, and sometimes there are safety hazards. For example, suppose you have two big rolls in which the operator has to put some material. Typically, such things are used in maybe used in thinning out kneading materials, like in the production of tires. Initially, rubber has to be kneaded before it can be molded in the form of a tire. So, in such cases, it is to be ensured that when the roll is rotating, the operator's hand is nowhere near the roll. So, that can be ensured very easily by requiring that to rotate the roll, you need to press two push buttons simultaneously. So, you are going to use both hands. So, you cannot make a mistake. So, for such cases, for example, let us see OR logic first. It is a very simple construction, pneumatic shuttle valve. So, you see that output, if you have pressure at this end, then you are going to get the pump connected to the system. On the other hand, if you keep pressure at this end also, then also this will shift this way. That is why it is called a shuttle. So, this will shift and close this one, it will take up this position and air will start flowing. So, here is OR logic, where even if you apply one of the pressures, then you are going to get the air flowing into the system. This is just an example which shows that by cascading these shuttle valves, you can have a 3 input OR gate also. So, at this point you have pressure applied when it is A or B, and then that is applied to one port. So, finally, the pressure is applied to the system when you have A or B or C. So, it is a 3 input AND OR, it is a 3 input OR. Similarly, these are realizations just to show that how these pneumatic elements can be used to generate various Boolean conditions. So, this is a realization of an AND gate using 3-way 2 position direction control valves. So, what happens is that when both these pressures are on, then this is in this box and this is in this box. So, therefore, the supply directly goes to the tank. Now, suppose this is not there, which means that now this is the position, but here it is there. So, therefore, you see that in this position this gets connected to this position, or rather this gets connected to actually this position, and no right rather this is connected to this position. You see, this is actually connected to this second side. So, actually it will not go there, it will rather go to the left one. So, then the system will be connected to exhaust if this is taken off. Similarly, if this is taken off, then what will happen is that the system will directly be connected to the exhaust. This is the exhaust. So, if any one of these inputs are taken off, then the system is going to be connected to the exhaust. Even if both are taken off, it is still connected to exhaust. So, it is AND logic. Similarly, that was realizing AND logic using two direction control valves, but you can also have a single element in which you can have AND logic. So, that this is such a construction, basically schematic. So, in this case, if you have either one of them is not there, then it is going to be, suppose this is not there, then this pressure is going to push this shuttle and bring it into flush with this, and this will be flush with this. So, this will be the position if y is not there. So, then you can see that both ports are cut off. Similarly, if x is not there, it will shift to the left, and then again both will be cut off. So, this will be there, this port can get the pressure only if both x and y pressure ports have been applied. That is why it is AND logic. So, as I was saying that this is you can have a safety application. So, in this safety application, only when both these pressures are applied will this cylinder get pressure. So, therefore, it cannot move. So, for example, there is some pneumatic cylinder coming down and probably pressing something, stamping something. So, you need to ensure that while it is stamping, by mistake your hand is not on your hand does not come on the ram. So, you can, so if you want to move the ram, which is the movement of the cylinder, then you have to press both these switches, right. Similarly, we show another application. This is a very interesting application where we are showing something like we are realizing something like a pneumatic latch. In digital electronics we have studied about latches. So, we are talking about a latch here. So, then what happens? We actually want to move this is the cylinder, or this is maybe it's a big DCV. So, we want to apply pressure here, that is our final objective, and the pressure comes from this line. Now, this you can see that this is it's a 3-way 2-position valve DCV, and this is, so suppose this is start PB. So, suppose I press this P. Initially what happens is that, see, this is the port. If this gets pressure, this will, then the valve will shift and be in this position. So, in this position the control pressure will go to the final load. So, we have to apply pressure to this one to finally apply pressure to this one. Now, when there is in the normal position, you see, when this is not pressed and this is not pressed, they are actually in this block and this block. So, this is directly connected through this to discharge. So, there is no pressure here. So, so there is no pressure here, when there is no pressure here, this is actually here. So, therefore, this pilot is also connected to exhaust, all right. Now, suppose the start PB is pressed. So, then it will be in this box. So, immediately this pressure will be applied through this shuttle will move, this is the shuttle valve. This shuttle will be pressed and air will flow in through this and it will create pressure. The moment it will create pressure, this valve will shift and come to this position, it will come to this position. When it comes to this position, this pressure, this gets connected and therefore, this gets pressure. Now, the interesting thing is that this push button need not be, one need not keep it pressed, because once the pressure develops here, that same pressure is going to be fed back, and this connection is wrong, fed back and it should be connected here. This connection is wrong. So, it is fed back here. So, now when this pressure is there built up, now if you release this pressure, release this, then it will get this part will immediately get connected to exhaust, and since there is pressure here, so this shuttle will be pushed and it will come to this position, and then this pressure itself will go through this and keep the valve in this position. Note that this is a spring loaded valve. So, if the pressure will be held. So, the pneumatic pressure is going to be held even if the start push button has been released, right. That is the point that we are trying to make. Now, if you want to reset this, how do you come out of this? So, you press this push button, this is the stop push button. So, what happens is that the moment you press this, this is going to be this valve is going to be shift here. So, then this is going to get exhausted. So, the moment this, now what happens is that this gets exhausted and this line which was coming through this gets blocked here. This is a normal 3-way 2-position valve. So, the pressure will go here and this valve will now shift to this box, which means that this pressure will now drain to exhaust. The moment this pressure drains to exhaust, then this is no longer in this position, but it is free. So, now if you again press the start push button, then again this can move here and energize. So, basically you see that we can, so this is a kind of latch where once the start push button signal is it is something like the auxiliary contact of a PLC logic or a latch in digital logic. So, even if you release the start push button, the pressure at this pilot port will be held, and therefore, this valve will maintain in this position and the pressure at this main load port is going to be maintained. So, this is one application which seems interesting. So, basically such things are realized using pneumatic logic. Now, we come to the actuator elements or the pneumatic cylinder. The pneumatic cylinders have lower force capability, but they have higher they have high speeds because they are generally driven against lower loads also, and this is not notion, this is motion. So, motion is not so precise because of the fact that there is the friction is higher and there is seals are tighter because to prevent air leak, so that the energy developed by the pump is not wasted. So, because of this high friction, there tends to be stick slip motion. So, the motion tends to be bursty, and precise motion control as is possible in hydraulics is not possible here. In fact, the applications are also less demanding. So, generally such precise motion control demands are also not there from the application side. Similarly, speed prediction is also complicated because they are actually complicated functions of pressure, temperature, etc., because we are talking about a gas here. So, there is a lot of compressibility issues. So, the speed prediction, the speed can vary a lot, and therefore, again that is also another reason why precise motion control may not be possible. So, in such cases one uses pneumatic cylinders, and they can be of various types. They can be single acting, where maybe spring loaded. So, from one side you apply the pressure, so it moves only this side. Retraction is maybe by a spring, generally it is by a spring, so that you actually do not require motion on the other side. If you have a double acting cylinder, then the connecting rod can move this way, that way, in both ways, and you apply. So, you can apply pressure on both sides of the piston. Similarly, sometimes it happens that you cannot, if you want to have higher force, then you cannot increase the cylinder area, either because of size requirements or because of speed requirements. If you increase the cylinder area, it takes more time for the air to flow. So, sometimes you put two cylinders in tandem like this with a common rod. So, you have a common rod, but you have two separate cylinders. So, you apply pressure here and exhaust here and here. So, on this surface some force will develop, on this surface some force will develop, F and F. So, total force on this is 2 F. So, two cylinders, effectively they are actually two cylinders are put in tandem. Sometimes such things are done. Similarly, you can have telescopic cylinders where separate, where you can have large stroke lengths. So, there are various such things are possible. We will not look at them in great detail. We will just see a picture of a pneumatic cylinder. So, this is a cylinder where this is cylinder body. You can see the piston and the rod which gets connected to the load. As we have said that you can put a flow control valve here. Sometimes you can put a quick exhaust valve here. So, this is a normal pneumatic cylinder. Similarly, you can have pneumatic motors, and they can be again of different types, positive displacement type, non-positive displacement type. So, you can have vane motors or you can have piston motors, just like we had in hydraulics. So, but these are used generally for low to moderate torque and high speeds, somewhat like electric motors. Generally, one advantage is that they can be easily stalled. Electric motors cannot be stalled because that will make a very large current to flow through these motors. There will be heating, etc. And it turns out that you can see that the typical kind of torque speed characteristics for pneumatic motors. So, initially the torque is low because of the available torque is low because of static friction being high, and then at some point of time as the static friction reduces, so the torque rises, and then after some time the so called linear or viscous friction takes over, and then at high speeds again a good amount of torque gets wasted in friction. So, the overall torque available characteristic falls for a given supply pressure. So, this is a picture for a radial piston motor. So, you see that if you apply pressure to these, pistons in sequence cyclically, then this, because of this mechanical arrangement, there will be rotational motion. So, this is naturally of a positive displacement type, that is in every cycle of the piston movement a certain amount of air goes through the system. Similarly, you can have non-positive displacement type. Here we have not shown a figure, but it is exactly similar to the vane motor of hydraulic systems in principle, although there may be constructional differences in design. Um, Another application is a 3-speed drive. So, in the 3-speed interesting. So, in the 3-speed drive we can quickly see what we are doing. So, you see that when suppose actually this is wrongly connected, it should have been here and this one should have been here. So, when it is in this position, then air flows like this, it goes through this, passes through the check valve. So, it does not pass through this or this. So, it goes like this and flows in, and then comes out through this path and will get connected. See, this is connected to this path. So, how much will be the speed depends on the rating of this flow control valve. Suppose it is F1. On the other hand, when it is trying to move this side from left to right, that is the position corresponding to this box of the DCV. So, now the DCV is going to get connected through this and this port will get connected here. So, it will flow through this into the cylinder freely, and then while coming out. So, while coming out initially it will see, this is a cam operated, this is a cam, actually this cam and this these are mechanical linkage. So, initially this cam is not operated. So, therefore, this is the position. So, it flows through the valve and returns and flows out through this path. So, the flow rate is F2. After some times, when this actuator moves out, this is going to operate the cam. So, operates, this will operate the cam and then the cam will shift. So, therefore, this valve will shift and go to this position and then will get locked. At that point of time, the flow will pass through this, because this is closed and this is also closed, this is a check valve. So, it will pass through this. So, after a certain time, the flow is going to be only 5, FPM means just feet cube per minute, that is a unit. So, it is going to be only 5. So, you see, so maybe this setting is F3. So, you can realize 3 settings, F1, F2 and F3 using this circuit, right, pretty good. So, as we have seen that pneumatic systems have one of their main drawbacks is that their time responses are slow, and basically happens because time is required to establish path of air. Air must flow into the final chamber and then time to develop pressure in the chamber. So, from the air source to the chamber, air path must be established and then pressure in the chamber must develop before something will move. So, these times depend on lot of factors like chamber volume, port pipe size, supply exhaust pressures, what is called the ratio of these upstream and the downstream pressures. Similarly, there are also these are times required for solenoid, coil inductance, inertia, etc. They are generally smaller compared to the pneumatic part, but all these factors will affect the time response of a pneumatic system. If you see the pressure, for example, if you see the pressure flow characteristics of pneumatic valves, it turns out that it depends on a number of factors. So, for example, it will depend on this is the weight flow rate, it will depend on discharge coefficient and area, that is standard for any flow, but because it is compressible flow, it is going to also depend on the upstream and the downstream pressures, particularly the upstream downstream pressure ratios. It will also depend on the temperature. So, these are special influencing factors for pneumatics. you know. So, it turns out that the in fact in this depends depending on the valve configuration, these upstream downstream pressures keep varying. For example, in a given situation, it may be so that the upstream is actually connected to supply, while the downstream is actually connected to load. This is load. So, see, if the load pressure varies, this ratio is going to vary. It may also happen that the upstream is connected to the load and the downstream is connected to exhaust. In this case, this is constant, but then this may vary. So, again the P d by Pu relationship will vary. So, in such cases, what is said is that if you want to have a constant flow characteristic, then you should maintain this P d by Pu ratio beyond a critical value. Actually, it should be less than a critical value, not greater than. This greater than is wrong. So, it turns out that so for example, you see that depending on the P d by Pu, if the P d by Pu, this function for a given, this function causes fluctuations in the flow rate depending on P d by Pu. So, but if you keep the P d by Pu ratio below a certain factor, like something like 0.5, then what happens is that this function becomes constant, and then the flow rate will only depend on things like one pressure, discharge coefficient, area, etc. That is, the flow fluctuations will be less. So, sometimes this P d by Pu ratio needs to be maintained. Similarly, if you see time response, then what happens is that, see, the whole air mass moves into the cylinder chamber, and depending on the capacity of the cylinder chamber and the flow rate and the air mass rate, you can have different kinds of, if you measure the pressure after a valve is suddenly opened, then if you measure the pressure variation with time, you can get various kinds of response. For example, for small chambers, it is going to be an under damped response. So, the pressure will build up, then it will overshoot and gradually settle to the real pressure. While if you have large chambers, sometimes this can be an over damped response. But in any case, a certain amount of time is going, for example, let us say so this much of time will be required before the actuation will take place. Now, we come to the last topic, which is the comparison of hydraulic, electric and pneumatic systems. So, turns out that for low power, low complexity, high volume applications, of course, generally pneumatic systems sometimes tend to give you an advantage. That is why it is used in things like using pneumatic tools in large assembly shops, like in an automotive factory. So, there you see these individual tools do not require low power, there is no complexity, general jobs are like screw driving, clamping, etc. But there are a large number of operator stations. So, what happens is that you can have a very low cost implementation of controls, because of the fact that the major equipment, that is a compressor, regulator, etc., they can be shared over this number of applications. So, you must have a high volume application, and the performance requirements are very ordinary. Some of the cost advantage comes because there is, as we have said, that there is no return line. So, that saves a lot of cost, half the tubing cost is gone. Just like hydraulics and pneumatics, there is no stalling problem, while in electric there is. In pneumatic there is no fire hazard. In hydraulic there is, because the oil itself is prone to fire, while in the case of electric, if the environment is if the environment is hazardous, then there can be fire, but in pneumatic there is no fire hazard. Generally in electric and pneumatic one has reduced temperature sensitivity because than hydraulic, because in hydraulic there is a the oil viscosity can change and give performance variations. In electric there is no question of viscosity, and in pneumatic the air viscosity change is not that predominant. However, hydraulic is mainly preferred when you have very precision motions and very high forces are required. That is not the case of pneumatic. In pneumatic, lower is used for lower force and pressure ratings for a given size. Response is slow for pneumatic, definitely slower than hydraulic, comparable to electric. In pneumatic there is a problem of leak, and leak is not so easy to determine, but it will reduce the efficiency of the system. This in turn will cause, if you want to prevent leak, you have to, that will increase maintenance cost. It will also make the seals tighter and will increase friction, which in turn will cause further fall in efficiency. So leak is a big problem for pneumatic systems. Interface costs may be prohibitive. Sometimes you may have to interface with electronics and other elements. So therefore, for very sophisticated controls, sometimes electric actuators may be preferred because they can be driven in using an all electric system. Lubrication is additionally required, while in hydraulic it comes along with the oil. So lubrication is required, and obviously motion control is less precise in pneumatics than either hydraulics or electric. So we come to the end of the lesson. We have seen pneumatic valves and actuators. We have seen some elements which are used in pneumatic logic. We have seen some typical pneumatic applications, and we have seen comparison with hydraulic and in some cases electric systems. So points to ponder. There are some questions like what are the main advantages of pneumatic logic. So we have already stated that, and what are the disadvantages? Obviously disadvantages in terms of speed and complexity. What is the benefit of quick exhaust valves? We have and can they be used in hydraulic control? Of course can't. They cannot be. Can pneumatic systems be actuated using PLC logic? If so, how? Actually, they are in many cases actuated using electric logic. Actually, this pilot actuation is typically, as we have said, that we have seen how a microprocessor can actually control a pneumatic system. So PLC is actually nothing but a microprocessor, as we know. So it can surely be used to control, but we might need, if you have an air pilot, we might need an I2P converter. That's all. Name an application where pneumatic control is more advantageous to hydraulic control. So I have given an application which is assembly tooling. You can think of others. So that's all for today. Thank you very much.